Does everyone hear me? Can you hear me okay? Yes, wonderful. So hi everyone, thanks for attending this talk. I'm Alexandre. I'm a PhD student from INRIA Rennes, and today I will present to you contextual equality saturation. So in one sentence, it's extending the technique known as equality saturation to better reason about programs using the conditionals in said programs. So before delving in, maybe I will present to you what is equality saturation through an example. So the main idea is equality saturation is automated reasoning on terms. So you have terms, maybe n plus 1 minus 1 and n, and you want to show that they are equal or equivalent. And your main tool to prove that terms are equal are what we call rewriting rules or equivalence rules. It allows you to say that certain forms of terms are equivalent to other forms. For example, any term of the form x plus 1 with x any term is equivalent to something s of x. So you are able to characterize many types of equivalence using this. You can characterize, for instance, the associativity of plus and minus, the fact that 0 will be the neutral of plus. And how we will use those rules through equality saturation is as follows. We will load our terms in what we call an E-graph, which represents equivalence classes of terms. So here you have minus, plus, n, 1, 1, and here you have n. In dashed lines, you can see equivalence classes of the terms. Right now, every term is in its own equivalence class. And my goal is to fuse this class up here and this one using my rules. So let's apply a rule. We see that we have n plus 1 in our E-graph, so we can apply the first rule. X plus 1 becomes s of x. So we add to the E-graph s of n in the same class as plus n1. So the main thing to remark in here is that this is a rewriting that is non-destructive. The old E-graph, this one, is still present in the new E-graph. So by applying my first rule, I didn't lose any opportunity to apply other rules. And so I can saturate the E-graph, enrich it with as many information as I want by applying every rule I can anywhere I can. So I will skip a few steps until we reach some form of some conditions that satisfies us, which is n is in the same class as our minus term initial. So to summarize everything I said to you, equality saturation performs rewriting on terms in the theory of congruence closure. It is parameterized by a rewriting rule set. And the general idea is you apply every rule you can, everywhere you can, until you are satisfied. It works on the shoulders of a powerful data structure called an E-graph, which encodes equivalence classes of terms. And it is very efficient in enabling rewriting. If you have a rule, you will know where you can apply it and how you can apply it. So more precisely, we can do automated reasoning with equality saturation, but we can also do automated program reasoning. So in 2011, Tate et al. Showed that you could design a term language to represent programs, and specifically the input-output relations of programs as terms. And therefore, you could reason about them using rewriting rules, using equality saturation. So this is powerful as it enables many applications, such as optimization. You have an initial program. You want to find an equivalent program that is more efficient in a way. Program analysis. And what interests us today, equivalence checking. So let's get into the problem that interests me precisely. I will want to validate some kinds of program transformations of a specific form. I want to correlate bodies of such form, x greater than or equal y to x greater than y. These two are not equivalent, but they are equivalent inside the check that x is different than y. So this is the form of program I want to correlate with this one. You can imagine different, maybe stronger transformations. This is the one I will use in this presentation. So I want to characterize this relationship. So I will design a rewriting rule that I will use in my rule set to characterize this equivalence. And so to design this rule, I will consider the simplest possible program that matches this form, in which inside the check you have only x greater than or equal y and x greater than y. So if I look at the E-graph that represents these programs, the terms representing this program, they look something like this. You get in here your greater than or equal xy, here greater than xy. Here's a check that x is different from y, and here you want to prove equivalent those phi terms, which I will explain now. So phi is a special type of term introduced by Tate, which allows to represent ternary conditional expressions, something that is sometimes wrote like this in the C language. The first child is a condition, and the second and third are the then and else branches. So if we look at a simple example, if x equals 5, then y becomes x plus 2, otherwise y becomes 6. It can be represented by the following terms. Phi of x equals 5, if so, x plus 2, otherwise 6. This is the output of y for the following program. So using these phi terms, I can design rewriting rules. So if I want to encode, as said before, this equivalence between a ternary conditional expression if x is different than y, x greater than or equal y, another point that doesn't interest me, and the same ternary structure with x greater than y, I can encode it using a rewriting rule using my phi symbol in here. And this rule can be applied to prove exactly that this term is equivalent to this one, the above I showed you earlier, which is good. So this rule works. I can prove, this is what is done to prove in standard equality saturation relationships between conditional programs, programs that rely on conditionals. So that's good, but there is something more I want of my rules, which is a form of universality. I want them to work on a variety of different programs. And here this one works on the simplest possible program matching my pattern. So let's consider a slightly more complex program. So you have the same general structure, ternary conditional expression, but the then branch is a bit more complex. You have your check x greater than or equal y, and you do the conjunction of it with a Boolean. So can I apply my rule in here? You will see that the different ingredients are here. There is a phi, the different forms, the greater than or equal. But actually, the rule requires that the second child of the phi term has the form term x is greater than or equal term y. This is not the case in here. This hand in here is blocking me. So you can deal with it, classically, by swapping the phi and the hand using an auxiliary rule that encodes some form of distributivity of phi over hand. So for something like this, phi of a condition C, x and y, z, can become the hand of phi cx z, phi cy true. You can check that if C is true, in here you get x and y, and in here you get, if it is false, you get z and true, which is z. So the rule is sound, it works. If I use it, I can swap the phi in here and the hand in here, and then I can use my rule. But it has a bit of problem. In general, these rules are called swapping rules. They do not scale. They pollute your rule set in a way that you need one rule per operator, and they lengthen your proofs. So earlier, I wanted to apply one rule, but to do so, I needed to apply an auxiliary rule. My proof is now twice longer. And remember that in equality saturation, I will apply every rule I can, everywhere I can. So if my proof is twice longer, this gives me more opportunities to apply irrelevant rules in other parts of my graph, and therefore it will tank my performance quite a lot. So can we do away with swapping rules? So this is the core of our contribution, which is a new type of rewriting rules we called contextual rewriting rules, which define what we call contextual equality saturation. So let's look at a contextual rewriting rule. You still get a general idea of writing a pattern into another one, but the pattern you get in here is slightly more complex than earlier. The pattern is divided between a contextual pattern, a check that must be made, and then you get the structural pattern, x greater than or equal y, which is the one you want to replace by the right-hand part of the rule. So what this rule encodes is the equivalence of these two structures. If you do a check that x is different from y, and then in an arbitrary then branch of this check, you have an occurrence of x greater than or equal y, you can replace this whole structure by a similar phi term with the same arbitrary then branch, but you have replaced greater than or equal by greater than. So this is a new type of rule entirely, which means I need to define how I will apply them in my graph. Equality saturation will work with them. So how can I find occurrences of a contextual rule in my graph? Well, a specification of how to do so could be to look for what I call contextual sources, so checks that my contextual patterns hold, phi of x different than y. And then I could do a traversal of the then branch, looking for my structural occurrence, x greater than or equal y. And then to apply the rule, now that I have found an occurrence, a path from a source to the occurrence, to the structural occurrence, sorry, I can copy this path below a new phi term, but at the end of the path I will replace my greater than or equal here by greater than. So this general specification allows me to solve the above problem of trying to apply my contextual rule in one step in my graph in here. So of course this specification is a bit naive. The core of our contribution is actually optimizing the specification with algorithms in order to apply contextual rules efficiently. And the key factor in equality saturation is what we call fail fast. Very often in a large E-graph, you will have no occurrence whatsoever of your rule before you do some other steps. And so we need to be able to quickly find that there are no occurrences of a contextual rule. The way we do so is with a new system of what we call E-graph annotations, in which phi terms in here will annotate the then branch with annotations that indicate that a path from a contextual source of x different than y exists above this class. The generality is that the annotation also allows you to find efficiently the path that exists. And so imaging looking for occurrence of your rule can now be done by looking for the structural occurrence and then checking in the annotation if or not a path exists. So if you want more details, you can find more in the paper, including algorithms on how to maintain these annotations, because any graph is a dynamic object. We will enrich it with new information, so we need to adapt our annotations to these enrichments. And you will also find details about the complexity analysis and an experimental evaluation that we made available in our artifacts. So a word about this evaluation, maybe. We made a prototype of equality saturation that implements both standard strategies and the contextual strategy we detailed in here. We tried it on synthesized benchmarks of increasing complexity to solve. Maybe the source is increasingly far from the target. Maybe you need to apply standard rules before you can apply your contextual rules. And we found that overall, contextual equality saturation was about 30% more efficient than the standard swapping rule-based approach. So in conclusion, we supplemented equality saturation with information from conditional propagation analysis, and we found it worthwhile for both expressivity, what you can say with your rule set, and efficiency. So there are future works possible on this, both these axes. On the side of expressivity, you could use the results from other static analysis and conditional propagation. And on the side of efficiency, initially what motivated us was building an equivalence checking tool for a specific translation validation from Java language to Kotlin language. So we could now implement this technology into such a tool. Thanks for listening.
Okay, thank you. Okay, so we have a few minutes for questions. Sorry, there is another one. And then.
Sorry. Yeah, so I was just curious, so SMT solvers make use of eGraphs and they also do like backtracking, trying different paths. So are there any applications of this to SMT solvers?
Oh, what you just said is eGraph are used in SMT solvers?
Yes.
I'm not a bit of an expert in SMT solvers. Not on the top of my mind.
Oh, okay.
Yeah, you could get a back and forth. We are using SMT solver technology for other ends, but you could figure a back and forth with what we figured in here back to the SMT. I could see it, yeah. Thanks.
Okay, so please.
Hi, so you have equality saturation with context now, so the obvious thing is bindings. Can you get bindings?
What do you mean by bindings?
Like variable bindings in the rules of equality saturation?
Oh, okay. Usually when the program representation we use...
Say you want to manipulate lambdas, right? Lambdas that bind variables.
Oh. Usually a term representation does away with variables. We no longer have any reference to them.
But you're adding context, so maybe you can have a better representation.
Oh, okay. That's an interesting idea.
Okay, thanks.
I don't have much to say about this, sorry. Thank you.
Thank you for the great talk. I would be happy to hear a little bit about the implementation details for this.
Yeah?
Oh.
About the implementation?
The implementation details. How you implemented it in code.
Okay. So I guess now we use the standard. We implemented an e-graph in general, but now we have an e-graph is supplemented with a map that maps each class towards an annotation table. Each class can have multiple annotations, and these annotations also hash const for better efficiency. I don't know what other details you want. We could talk with later, maybe.
No, that's it. Thank you.
Thank you.
Well, thank you. So thanks again. So maybe while we are swapping laptop, I think Barry wanted to ask a question. I mean, maybe quickly.
Another question?
Switching laptops, maybe.
My question is how this work relates to conditional rewriting.
Okay. As in directly in the program, you would rewrite conditions?
Well, there's in the rewriting community, there's been a substantial amount of work on conditional rewriting, and perhaps your work is built on top of that, or better or worse. I was wondering if have you made a comparison?
Not on the top of my mind, but I would say my work is more built on top of this.
Right. Okay.
Thank you.
And